My name is Ryan, and stock market next day forecasts with sentiment and technical analysis using machine learning. Stock market forecasting remains a complex and challenging task to forecast. Traditional technical analysis methods like RSI, EMA, and candlestick patterns often fail to analyze the stock market time series pattern. Many recent studies have now explored forecasting using machine learning or neural networks. Other studies have improved the increase in accuracy or decrease in regression loss by applying technical indicator and sentiment analysis. This paper aims to analyze the performance of machine learning models in predicting the stock market's next day trend by incorporating both technical and sentiment-based features. Due to that dataset limitations, specifically financial news articles, neural networks were tested and showed no significant improvements in learning. So neural networks were not utilized and traditional machine learning models were employed instead. Technical indicators were derived from Benzinga Pro as a reliable financial news source. A variety of machine learning models such as XGBoost, gradient boosting, random forest, decision tree, k-nearest neighbor, support vector machine, and logistic regression were trained to assess its predictive performance. Result indicates that logistic regression outperformed the other test machine learning models with an accuracy score of 0.679. These reports highlight the effectiveness of combining sentiment and technical features to enhance stock market predictions accuracy. However, limitations such as news data availability remain a key challenge that could potentially increase the performance of the model. Future research could experiment with alternative models and more news datasets. The continually evolving landscape of financial markets necessitates advanced methodologies for predicting stock prices. Traditional approaches, primarily based on statistical and econometric models, have often struggled to deliver accurate forecasts due to complexities and nonlinearities inherent in market behavior. This limitation has inspired increased curiosity in machine learning techniques, which offer enhanced predictive capabilities by leveraging large datasets and sophisticated algorithmic frameworks. As financial markets are increasingly influenced by social media sentiment and public perception, incorporating sentiment analysis into predictive models has emerged as a vital enhancement. With prior research has shown that public sentiment can significantly affect stock price trends, with upward price movements associated with positive sentiment and falls with negative sentiment. Other prior literature has pinpointed essential technical indicators variable affecting stock pricing, such as the candlestick patterns, Bollinger Band, and relative strength index, and of course, moving averages. Highlighting the importance of integrating these indicators with machine learning algorithm for improved predictive accuracy. The pressing need for more reliable stock market forecasts underscores the importance of employing multifaceted approaches that integrate sentiment analysis and technical indicators through machine learning techniques, potentially improving accuracy result even further. The dataset used in the study are price and sentiment. The price dataset used are the E-mini Nasdaq 100 future, the E-mini S&P 500 futures, E-mini Dow Jones futures, the volatility index as VIX, and dollar index as DXY, adjusted without bank holidays, weekends, and half days obtained from the Chicago Mercantile Exchange. It ranges from 5th April 2002 till 13 September 2024, with total count of 5,648 rows, whereas the news dataset collected from Benzinga Pro using Alpaca API, these two datasets are converged, syncing the dates with real trading day. The merged dataset date now ranges from 5th January 2015 to 10th September 2024. Because of the website's own limitation, we were able to collect only a total of 2,437 rows. The next day direction for each day is calculated by taking the closing price difference from today and tomorrow of that specific date, then converted into binary 1 for next day uptrend and 0 for next day downtrend. This new column is applied as the categorical target variable for the model to predict. Then, the merged dataset is divided into training and testing set. 80% training and 20% testing. The dataset is then normalized using a standard scaler for both non-stagnant and stagnant features to keep it simple. The main technical use in the study are short-term swing, ST, intermediate-term swing, IT, and long-term swing, LT. They're then compared against the traditional baseline like RSI and EMA. The identification of short-term swing is created when there's 3 rows of open, high, low, close, and the first and third row high is lower than the second row high, creating what's known as a short-term high. Then using the newly created swings, the trend of the price open, high, low, close is found by signaling the value of 1 for swing high activation or 0 for swing low activation. This is done for all 3 of the swing types into a column. When the swing high is activated most recently, it signals that price is now trending bearish, and it amplifies when an intermediate term swing high or even a greater long-term swing high is activated. The news data is interpreted with a sentiment reader called FinBERT, which is a finance-specific variant of BERT, just the bidirectional encoder representation from transformers. It's pre-trained specifically on financial text, and its purpose is to process natural language processing tasks in the financial domain. With it outputs the sentiment score and label, which are put into column inside the dataset for training. This technical and sentiment dataset combined is normalized and resampled using SMOTE to rebalance the data imbalances from uneven class distribution of target variables as seen in the picture on the left. Before SMOTE, we could see our class variable, which is 1 and 0, for the model predict, has 0.549 and 0.450. And after data rebalancing using SMOTE, we can see they're both balanced perfectly 50-50. Then, this study employs 6 supervised machine learning models to examine and find patterns in the dataset. In order to classify data, support vector machines identify the best hyperplane to maximize the margin between data points of distinct classes. Logistic regression is applied as a probabilistic model to estimate the likelihood of categorical outcomes. K-nearest neighbor is a non-parametric technique that effectively recognizes patterns by classifying data points according to the majority class among the KNN. And then decision tree is used as a baseline model, employing a tree-like structure for decision-making based on feature splits. And to enhance predictive performance, ensemble methods like XGBoost, gradient boosting, and random forest are implemented. Random forest constructs numerous decision trees and averages their forecast to reduce overfitting. Gradient boosting sequentially corrects errors by training weak models iteratively, improving accuracy. And then XGBoost, an enhanced version of gradient boosting, is employed for its efficiency and regularization capabilities, making it robust against overfitting. Model evaluation is based on metrics like the confusion matrix, F1 score, recall, precision, and accuracy to ensure optimal selection for deployment. And as seen here from our experiments, we have first the sentiment-based model performance. The financial news article collected from Benzinga Pro is interpreted using FinBERT and merged with the E-mini Nasdaq futures and the other intermarkets. The performance here is shown on the left, with total accumulated accuracy of 3.702, total accumulated F1 score of 8.34, and with the best performing model, which is the gradient boosting, with 0.55 accuracy score. Then on our second, we have the relative strength index. The RSI is a lagging technical indicator to measure momentum that oscillates. It does this by measuring the speed and magnitude of a security's recent price alteration to identify overbought or oversold circumstances in the security's price. The RSI is overbought if the value reaches above or equal to 80, and is oversold if the value reaches below or equal to 20. RSI overbought, oversold model performance is shown as total accumulated accuracy of 3.639, total accumulated F1 score of 3.792, and best performing model gradient boosting with an accuracy score of 0.569, which is better than our sentiment-based score. On our third, we have the exponential moving average. The EMA is a lagging technical indicator, lagging, and is used to track price trend using a specific period. EMA is a weighted moving average, therefore it places important in most recent price data. The model used two EMA period, the 10-period EMA and 20-period EMA. These two are then converted into either uptrend or downtrend. When the 10-period EMA crosses above the 20-period EMA, this signals an uptrend. And when the 10-period EMA crosses below the 20-period EMA, this signals a downtrend. The EMA trend model performance is shown with total accumulated accuracy of 3.721 and a total accumulated F1 score of 3.994 and a best performing model of gradient boosting from all the 7 models previously. In our last experiment, we experiment with Dow theory, which is the short-term, intermediate-term, long-term swing as trend, and is a non-lagging technical indicator, non-lagging, to define a trend in the market. An uptrend is found by the creation and support of a long-term low, intermediate-term low, then a short-term low. An uptrend is stronger when it creates those while breaking through the highest short-term high, intermediate-term high, and long-term high. The performance and visual of the three-swing model is as displayed. As you can see, we have our long-term swing low as the red dot, and our intermediate-term low as our orange dot, and lastly, our short-term low as the yellow dot. This model performance, with total accumulated accuracy of 4.462 and total accumulated F1 score of 4.81, and with the best performing model out of all the experiment with logistic regression with an accuracy score of 0.679, beating all the other models' performance. This highlights the efficiency and capabilities of short-term, intermediate-term, and long-term swing models in technical analysis. In conclusion, the logistic regression model, which incorporates sentiment analysis and the three swing technical indicators, short-term, intermediate-term, and long-term swing, outperforms all the other test machine learning models with an astounding accuracy of 0.679. This highlights the significance of integrating both sentiment and technical analysis in predicting stock market, specifically NASDAQ next day trend. Despite these encouraging results, there are still certain limitations that must be recognized as the relatively small dataset restricted the use of more complex models, such as deep learning, which may have provided even greater predictive accuracy with a larger training data. Future improvements are possible by incorporating alternative models, including the three-swing model as technical indicator, and adding more financial news dataset to potentially allow neural networks or other deep learning models to learn properly.